Welcome back to a physics session. It's a concept session in which we are going to discuss system of particles, rotational motion and oscillations. Let us see the lesson structure first. What are we going to discuss under system of particles and rotational motion? They are center of mass, moment of inertia, angular momentum, force torque, then rolling motion we are going to discuss under this system of particles chapter. Later oscillations separately we will discuss in the same session. Translational motion means a straight line motion. That is a translatory motion. A motion of a body is called translatory if a line drawn between any two of its internal points remains parallel to itself during the motion. Of course, you can feel that it's a straight line motion. And in pure translational motion, at any instant of time, all particles of the body have the same velocity equal to that of the center of mass. Pure translational motion, center of mass velocity and all the particles velocity will be same. Simply speaking, suppose a train is moving, then train's particles velocity and center of mass velocity will be same, like that. And rotatory motion means a rigid body is said to be in pure rotation if every particle of the body moves in a circular path about common center or multiple centers. Circles lie on a straight line called the axis of rotation. So if the particles are moving in circular paths, then their centers will lie on a same straight line. That is known as, I can picturize that. Suppose here is a body. Here I am taking the pen. Suppose here is a body. This particle is moving in this circle and this particle moving in this circle. This particle is moving in this circle. Then it's a center. All the centers are lying on the same straight line. This is axis of rotation. That's what. Hope you understand. Yeah. Next. All points in the body which are perpendicular to the axis of rotation turn through the same angle in the same time interval. Angular displacements are same for a given time interval. Angular displacements are same for a given time interval. In rotational motion, the line joining any two internal points do not remain parallel. Line joining any two points do not parallel to itself in the rigid body system. Center of mass. Center of mass of a system of particles is that single point within the system boundary, but not within the body, within the boundaries of the body, which moves in the same way. A single particle endowed with the whole mass of the system and subjected to the same external force will move. So entire mass behaves like is concentrated on one point. That point is known as center of mass. Center of mass is a location, not mass. Next, any force exerted at the center of mass may produce linear acceleration of center of mass, but it cannot produce rotation. If you apply force at the center of mass, through the center of mass, then it will produce only translatory motion, but not rotatory motion. But if you apply force other than center of mass location, then definitely it will get, if the force extended line is not passing through center of mass, then it causes rotatory motion. If the force extended line is passing through the center of mass, then it causes only translatory motion. Yes. Next, center of mass of a body is at its geometric center for small symmetric objects. Need not be symmetric for small objects. All small objects, geometric center is the centroid. What you call center of mass. Yeah. Center of mass of a body or system of a particle depends on the mass and distribution of the particles in the system. The internal forces of the system do not change the position, velocity and acceleration of the center of mass. External forces only can change location, velocity, acceleration of the center of mass. The position of the center of mass of the system does not change with the change in coordinate axis. Suppose one body is having center of mass at one location. If you observe from coordinate system fixed at one corner of the room, center of mass of the body will be there only. Suppose another system if you consider, then center of mass are there only. So center of mass remains will be at the same place irrespective of the coordinate system. The algebraic sum of the moments of masses of all the particles about center of mass is 0. So sum of moments of masses about center of mass is 0. Acceleration of center of mass is net external force by total mass. And in the absence of net external force, velocity of center of mass remains constant. That is Newton's first law. Matter may or may not exist at center of mass. Matter may exist, may not exist. Suppose there is a ring. There is no mass at the center of mass. So center of mass may contain mass or may not contain mass. When a body or system of particles is situated in a region where the acceleration due to gravity G remains constant, then center of mass coincides with center of gravity of the system of the particles. Next, suppose center of mass of two particle systems separated by distance d is given by, see, center of mass is here. Let me take a pointer. Yeah, center of mass is here, mass m1 is here, then distance of center of mass from m1 is m2 d by m1 plus m2, m2 d by m1 plus m2. Similarly, r2 is equal to m1 d by m1 plus m2, and r1 by r2 definitely equal to m2 by m1, because algebraic sum of moments about center of mass is 0. So r1 m1 equal to r2 m2, r1 m1 minus r2 m2 equal to 0. That's why. And center of mass is situated always near to a heavy body, remember. Next, RCM is equal to XCM I cap plus YCM I cap plus ZCM K cap. Of course, it's a normal coordinate system with position coordinates. Next, if it is a distributed mass system, then we can take center of mass location is 1 by m integral x dm. 1 by m integral x dm for distributed mass systems. And for coordinate systems, if you know, then m1 x1 plus m2 x2 by m1 plus m2 you can use. Motion of center of mass, just m1 v1 plus m2 v2 plus m3 v3 by m1 plus m2 plus m3 and so on. Next, acceleration of center of mass will be differentiation of that, so that m1 a1 plus m2 a2 and so on by m1 plus m2 plus m3. Next, circular ring at the center of the ring. Yes. Next, circular disc at the center only. Thin uniform rod at the center only. Triangular plate, centroid, center of mass locations. Square plate, centroid, diagonals intersection. And at the point of intersection of diagonals for square plate as well as rectangular plate. Hollow solid sphere, center. Hollow or solid sphere will be center. Next, solid cone, h by 4 from the base. And hollow cone h by 3 from the base, h by 4 from the base, h by 3 from the base. Hollow cone h by 3, solid cone h by 4. So who is more stable? Center of mass must be close to the base, then only that is only the stable one. H by 3, h by 4, which is smaller? 1 by 3 means 0.33, 1 by 4 means 0.25. So which is obviously solid cone is most stable. Yeah, at the midpoint of its axis, which one? Solid cylinder. And arc, this one, an arc of radius r subtending an angle alpha at the center of curvature at a distance from its center of curvature and the axis of symmetry, that is 2r by alpha sin alpha by 2, 2r by alpha sin alpha by 2. At that place from the axis of rotation it is going to locate. Next, and a semicircular arc of radius r, semicircular arc of radius r at a distance from its center on the axis at 2r by pi distance, 2r by pi. From O it is 2r by pi. And a quadrant of a circle, if it is, then 4r by pi root 2, 4r by pi root 2. Yes. Next, 4r by pi root 2. Still 3 more. Semicircular disc 4r by 3 pi, semicircular disc 4r by 3 pi, and solid hemisphere 3r by 8, hollow hemisphere r by 2 from the O center. Okay. Next, angular velocity. Average angular velocity of the particle is given by change in displacement, that to angular displacement by change in time. If you take time interval larger, then average angular velocity will come. If you take time interval smaller, then instantaneous angular velocity will come. So instantaneous angular velocity is nothing but rate of change of angular displacement. And V bar is equal to omega bar cross R bar is better one to memorize. Don't memorize V equal to R omega. Memorize V bar equal to omega bar cross R bar. That is vector notation, a correct representation. Then omega equal to V by R, and V must be perpendicular to R. Then only you have to use this expression. Otherwise you have to go for V sin theta by R. Next, alpha is equal to, what is that alpha? Angular acceleration. Alpha equal to rate of change of angular velocity. Just it is, see, S by T is velocity and A is equal to dV by dt, right? dV by dt. This is ds by dt. Similarly, omega is equal to d theta by dt and alpha is equal to d omega by dt. So very similar, linear acceleration, angular acceleration, linear velocity, angular velocity, similar things. Torque. Torque is analogous to force. Rate of change of linear momentum is torque. Rate of change of angular momentum is torque. So torque is analogous to force. Moment of force is called torque. Torque is equal to R bar cross F bar, R bar cross F bar, RF sin theta, and torque is an axial vector. Some more points about torque. A pair of equal and opposite forces with different lines of action form a couple. Couple is a subcase of a torque actually. Whenever two torques are there, then we will call it as a couple. Couple produces rotation without translation, and moment of couple is equal to either of the force into perpendicular distance between the two forces. Next, the moment of couple is independent of choice of origin. This is angular momentum expression. Angular momentum is equal to R bar cross P bar, R bar cross P bar. So sin theta is, I have to give like this, L bar L is equal to RP sin theta. Sin theta must be here, not here. Sin theta must be here. L bar is equal to RP sin theta, as it's a cross product. A cross B equal to AB sin theta, right? Like that. Next, it is also an axial vector. Along the axis it exists. And the torque, angular momentum are related as tau external equal to dl by dt. This is just like rate of change of angular momentum. And principle of conservation of angular momentum states that net external force on a system, net external torque on a system. Why? Because it's law of conservation of angular momentum. So what I can say is net external torque on a system, is 0, then the total angular momentum of the system is conserved. Just I reduced the lighting. Yeah, a body is said to be translational motion if vector sum of all the forces acting on the body is 0. Similarly, if vector sum of all the torques acting on the system is 0, then the body is in rotational equilibrium. Next, lever. Rod AB is a simple lever where R is the fulcrum, the picture you see. R is the fulcrum, rod AB is a simple lever. One side load arm, one side effort arm. We are going to apply force on other one end, that is called effort arm, and load we are going to fix, that is load arm. Distance D1, distance D2. As the more distance of the effort arm, then less is the effort. More the distance for effort arm, then effort will be the lesser one. Principle of moments is D1 F1 is equal to D2 F2. Mechanical advantage is F1 by F2 is equal to D2 by D1. Next, moment of inertia is measured in terms of, moment of inertia is nothing but rotational inertia, and analogous to mass in linear inertia. Mass is the measure of linear inertia. Moment of inertia is a measure of rotational inertia, whose formula is given by mr square or mk square. K is known as radius of gyration. And moment of inertia for different bodies. Thin circular ring mr square, thin circular ring of radius r, this is circular disk of radius r. Okay, along the diameter, the body is same, the axis is changed here. Axis is along the diameter. Let me change the color. Yeah, along the diameter mr square by 2. Along about an axis, okay, pictures will be there. Yes, yes, with the pictures it's somewhat sense and meaningful. A rod ml square by 12 and perpendicular disc mr square by 2. Yes, with the pictures it sense. Otherwise I try to draw. Yeah, so ring diameter, this is circular disc, but picture is ring. Haha, have to draw. This is disc only, then only mr square by 4, disc mr square by 4, and hollow cylinder mr square only. Hollow cylinder should be treated as ring over ring. Solid cylinder should be treated as disc over disc, so mr square by 2. And solid sphere 2 by 5 mr square, 2 by 5 mr square, 2 by 5 mr square is solid sphere. 2 by 3 mr square is a hollow sphere, that also will come. Okay, this is perpendicular axis theorem. That didn't come, so I will write there only. 1 minute. Yeah, because hollow sphere is also important, right? Hollow sphere is 2 by 3 mr square. Okay, hollow sphere 2 by 3 mr square. Next, perpendicular axis theorem. Perpendicular axis theorem is applicable for planar laminas. Perpendicular axis theorem applicable for plane laminas. It has a limitation. Only laminas, planes, it is applicable. Suppose this is Ix and suppose this is Iy, then this is Iz. Iz is equal to Ix plus Iy. Iz is equal to Ix plus Iy. And parallel axis theorem will be applicable for any body. A body, then this moment of inertia is given by center of mass axis moment of inertia plus mx square, mass of the body, and x is the distance between them. So that is, okay, here I wrote mr square, no problem. This kinetic equations, omega equal to omega naught plus t, theta equal to omega t plus half at square, omega square equal to omega naught square plus 2 alpha theta. Nothing but v square minus u square equal to as only. Okay, so like we will go. Next, work done by torque W is equal to integral tau into d theta. Work done by the torque integral tau into d theta, just like integral f dot ds. Power is equal to rate of doing work. Here rotational power is equal to rate of doing rotational work. And torque power is equal to force into velocity, torque into angular velocity. And torque is equal to r bar cross f bar equal to I alpha. And work energy theorem, half I omega square minus half I omega naught square, change in kinetic energy, work done. And angular impulse, I is equal to tau into dt. All the formula you have to refresh in your mind, write 5 times, 10 times, try to learn, try to practice, so that time management will be easy in the examination. First you need to understand how those formulae are obtained. The derivation also you need to know. At the same time you need to practice the formula. Rolling motion related things are combination of translational motion as well as rotational motion. That means rotating and moving forward. So translation will be there, rotation will be there, both will be there in rolling motion. Rolling motion means translation as well as rotation. The point of contact of rolling body with the surface has no relative motion with respect to the surface. That is pure rolling. Point whatever in contact with the surface of a rolling body then is not moving, momentarily at rest, then that is known as pure rolling. And that only we have in our syllabus. Slipping and skidding we don't have actually. That is in higher classes, we will discuss. Condition for pure rolling on the surface or plank is this one only, second point only. That is equal to VCM is equal to R omega. VCM is equal to R omega is condition for pure rolling. If plank is moving with constant velocity, then condition for pure rolling is V minus R omega is equal to U. And if the plank is moving towards left, that means in a opposite way, then R omega minus V is equal to U. Plank is moving with constant velocity U towards right, then That is this one here. If the plank below the body there is a plank, if the plank is moving to right side, then V minus R omega must be U. Pictures are there, fine. Then you can understand in a better way. That is V minus R omega is backwards. So V is forward. V minus R omega, center of mass velocity and the plank's velocity must be same. So V minus R omega is equal to U, that is pure rolling. And in the other case, R omega minus V is equal to U, then also pure rolling will be obtained. Next. Condition for non-uniform pure rolling. Acceleration is equal to R alpha, non-uniform pure rolling. And kinetic energy equal to half I omega square. In rolling, there will be translatory motion, there will be rotational motion. So, for kinetic energy sake, you have to think two kinetic energies. One is rolling kinetic energy. Rolling kinetic energy is nothing but rotational kinetic energy plus translatory kinetic energy. One is rotational kinetic energy, half I omega square. Other one is translational kinetic energy, half mv square. So, both together will give you rolling kinetic energy, because rolling has two types of motions. Next, kinetic energy translational by kinetic energy total is 1 by 1 plus k square by r square. Kinetic energy rotational by here I would like to write in a better way so that you can enjoy it in a different way. Kinetic energy translational half mv square, half mvcm square. Yeah. Kinetic energy of rotation, only rotation, then half I omega square, half I omega square. This is half mv square of 1 plus just k square by r square, k square r square. Yeah. Next, kinetic energy of rolling, sum of these two, kinetic energy of translation plus kinetic energy of rotation. So that is going to become half mv square of 1 plus k square by r square. So from this onwards, 1 divided by other one, anything you can get. So it's not a big task to understand or to memorize. Next, angular momentum. Angular momentum L is m into r bar cross v bar with different axes. If you want that, this expression you can take. Still many points are there. Okay, I'll erase this and I will continue with. On an inclined plane, if the body is rolling, then velocity before touching the ground is square root of 2gh by, actually acceleration for this case is acceleration is equal to g by 1 plus k square by r square. This is the acceleration. So wherever root 2gh is there, wherever g is there, there you have to write g by square 1 plus k square by r square. Then automatically everything will come. Velocity is root 2gh. Time is square root of 2h by g. So square root of 2h by g, h can be taken as length of the plank, then 2l into g sine theta by, of course if you are taking the length instead of h, then sine theta also will come. So g sine theta for length of the plank, okay, g only for h, g refers to h, g sine theta refers to length of the plank, because if you are thinking direct displacement, height h, then g you have to take. If you are thinking along the plank L, then g sine theta I have to think. That's it. So this is g sine, oh, it's there, it's okay. Now T is equal to square root of 2L of 1 plus k square by r square by frictional force F is equal to mg sine theta by 1 plus r square by k square. Minimum value of quotient of friction for a body to follow pure rolling on inclined surface with inclination theta from horizontal, mu is equal to tan theta by 1 plus r square by k square. It is not k square by r square, it is r square by k square. Yeah, mu minimum is equal to, or mu should be what you call greater than or equal to tan theta by 1 plus r square by k square. This is 1 plus 1 by c we usually call. If the force is applied at any other point on a body, then acceleration is equal to f by m into 1 minus rx by k square, where x is the distance about the center of mass line and the force application. If k square is greater than, friction backwards. If k square equal to rx, no friction acts. If k square less than rx, then friction acts forward. Depends upon that, the body's tendency will be there. Oscillations we are going to discuss. Subtopics. That means this session covers these points. Characteristics of SHM: loaded spring, simple pendulum, and various different types of SHMs. We'll see. Periodic and oscillatory motion. First, what is oscillations? That means periodic motion, oscillatory motion, later SHM condition, then SHM characteristics. The motion which repeats at regular intervals of time is called periodic motion. Regular intervals of time motion must be repeated. That is periodic motion. Next, periodic motion in which a body moves to and fro about a fixed point is called oscillatory motion. And motion of a particle is said to be simple harmonic. If these conditions happens, it must be to and fro motion. Its acceleration must be proportional to the displacement, and that means the displacement and with a negative sign. That means acceleration is always directed towards a fixed point. Acceleration is directly proportional to the displacement and opposite to it. So A proportional to minus y. A is proportional to minus y. Or in an equation, constant is omega square. A is equal to minus omega square y. And equation of SHM is A plus omega square y equal to 0. This is equation of SHM. Okay. Now, all vibratory motions are periodic, but all periodic motions need not be vibratory. Motion of Earth around Sun is periodic, but not vibratory. It is not coming back. And example of a simple harmonic motion: simple pendulum, motion of a needle in a sewing machine, and motion of a prongs of vibrating tuning fork, vertical oscillations of a loaded spring. Condition for a body to be simple harmonic is that restoring force must be linearly dependent on displacement. Whenever restoring force depends on displacement linearly, then acceleration will be proportional to displacement, automatically comes. So for different SHMs, the conditions are given. Restoring force mg sin theta, mg theta directly proportional to f. F is equal to minus kx, c equal to minus tau theta. So that they are SHMs. And equilibrium position, the point at which no net force acts on an oscillating body, is known as equilibrium position, and there the minimum potential energy will exist and maximum kinetic energy will come. That is mean position. Extreme position, where the maximum restoring force acts, that is extreme position. Representation of SHM. An SHM is represented with a displacement equation y is equal to a sin omega t plus r minus phi, where a stands for amplitude, omega t plus r minus phi is known as total phase, and phi is just initial phase. And if the motion starts from mean position, so phi must be subtracted from omega t. Here particles started early in the third one, so phi must be added. See, omega t is this one. I will give you, wait, red color I want to take, red color, this is suppose a omega t, then phi must be added to it, omega t plus phi, and this is here to here is omega t, this is omega t, so this phi must be subtracted, omega t minus phi in this case, this is omega t plus phi. Okay, so initial phase is a correction. I already wrote. Yes, I excited. Next. Where are we? Sine function. Huh? If the phase is 0, the particle is crossing the mean position. Yes. If the phase is pi by 2, the particle is at extreme position. And example, y is equal to a sin omega t plus pi by 4 at t equal to 0, then phi is equal to pi by 4. Yes. And just a minute. Next. If the motion starts from the extreme position, then phi equal to pi by 2 you have to add up. Obviously the function will become a cos omega t. So if you are observing y equal to a cos omega t, the motion is starting from extreme. If you are observing y equal to a sin omega t, motion is starting from mean. y equal to a sin omega t plus b cos omega t, then SHM can also be represented in the following ways. F is equal to minus ky, that is equal to ma, and E acceleration is d square y by dt square, so that this is the SHM equation. Next, characteristics of SHM. Some more points. Amplitude, maximum displacement of the particle, and SI units is meters only, and then amplitude can be square root of x2 minus x1 whole square plus y2 minus y1 whole square, and so on by the number of events, whatever you have. Next, at the extreme position, extreme displacement maximum, velocity minimum. Extreme means you can always imagine simple pendulum. Extreme velocity 0. Acceleration of the body is maximum. Potential energy of the body is maximum, and kinetic energy minimum because velocity is minimum. Next, graphs. Oh, let's go back. Yeah, displacement time graph, sinusoidal function will be like this. If it is a cos function, that will come like that. Differentiation of it will give you a omega cos omega t is a cos function, so cos graph will come. And acceleration time graph, acceleration time, see acceleration negative, right? Minus a omega square, that's why it starts from bottom onwards. And this is acceleration displacement graph, acceleration displacement graph, that's why this way, acceleration positive, displacement negative, displacement positive, acceleration negative, that's why it will be in second and fourth quadrants and the respective things. Next, this is force time graph. Displacement, velocity, acceleration and force acting on the body vary with time, but their values repeat themselves at regular intervals of time. They vary with time, but they repeat the same values with regular intervals of time. And kinematic equations cannot be used to solve these things. So you have to go for different things with the help of a reference circle. So those things we are going to discuss. A horizontal board moves to and fro in the vertical plane. Horizontal board moves to and fro in the vertical plane. SHM of amplitude A, then its time period is given by 2 pi root A by G. And when the board is at the highest position, normal reaction force is mg minus m omega square A. And when the board is at the lowest position, then mg plus m omega square A will be normal reaction force. Next, if n1 is equal to 0, body ready to leave the surface, then so which we obtain the time period of oscillation and everything. A horizontal board moves to and fro in the horizontal plane like this, then amplitude A, then things as usual. T is equal to 2 pi root A by mu G. Mu is quotient of friction. If there is no quotient, then the formula will take another form. And potential energy is half m omega square y square is the potential energy. Half m omega square A square sin square omega t plus phi plus or minus phi you can take. And potential energy graph will be like this, and potential energy displacement graph will be like this. See here, square is there, that's why potential energy graph is in the positive side of the time. Okay, next, potential energy minimum at mean position, potential energy maximum at extreme position. Always you think about simple pendulum, that will be better to you. During one complete vibration, average potential energy is given by 1 by 4 m omega square A square. Next, the kinetic energy of a particle in SHM is given by Ke equal to half m omega square A square minus y square. And these are all variety graphs. You need to practice all the graphs at a time so that you come to know in a better way. Mean position, kinetic energy maximum; at extreme position, kinetic energy minimum. These two things you need to understand. And kinetic energy, position displacement function is A square minus y square, and the time dependent function is half m omega square A square cos square omega t plus or minus phi. Next, total energy is constant, half m omega square A square. Total energy has no frequency, infinite time period. It's a constant value, and its graph will be like this. It's a time dependent horizontal line. It won't change, that's why. And position dependent also, it won't change. It's a horizontal line. Next, total energy of a particle in SHM is independent of the position. simple pendulum. In simple pendulum, tension in the string at any position is given by T is equal to mg cos theta plus mv square by L into A and mv square by R, like mv square by R. Next, V equal to 0, then tension in the string will become T minimum, that is equal to mg cos theta only, that is at extreme position. What is the tension? Mg cos theta. When the bob is at mean position, tension will be maximum, that is mv square by L plus mg. Here it is not A, this is just mv square by L only. And yes, that is end. Yeah. Next, name of the topic, I will name V is equal to root 2 GL of 1 minus cos theta. This is simple pendulum only. Name of the topic is here simple pendulum. Simple pendulum. If theta is the angular amplitude of the simple pendulum, then the maximum tension in the thread T maximum is equal to mg of L plus theta square. That is equal to A by L whole square. Yes. Next, linear amplitude and blah blah blah. This equation is SHM equation only. Because it obeys SHM. Time period is equal to 2 pi root L by G. Seconds pendulum time period is 2 seconds. Yes, you are right. Next, time period independent of size, shape, mass of the bob, and time period is constant for the given length of the pendulum. Provided amplitude is small, it is independent of amplitude also. And time period is from T equal to 2 pi root L by G. As per that, the three laws can be derived. Those three laws are known as Galilean laws. Only two, T proportional to root L, T proportional to root G, and the third one is this one, the top one. That is size, shape, mass, independent things for time period. Next, there are two graphs for simple pendulum. One is TL graph, other one T square L graph. T square L graph is a straight line, TL graph is a parabola. Okay. Next, one more graph came up. Yeah, this is combined graph, and the intersecting point is time period 1 second. T square is also 1 only, no, that's why. And at that time, that means time period 1 second, then length of the pendulum is 25 centimeters. But seconds pendulum's length is 100 centimeters. Seconds pendulum length 100 centimeters. T equal to 1 second corresponding length, yes, 25 centimeters, 1/4 of the meter. And these are all some points which I will read. When a pendulum is taken from the earth to moon, its time period increases because G value decreases. If the bob of the pendulum is made hollow and filled with water, and water is drained slowly, that I have to draw a picture here. Suppose the bob of the pendulum is like a bar like this and is suspended. Then if you are emptying this slowly, then center of mass of the pendulum will be here first. As you empty, it comes down, down, down. Later again it goes up, up, up and comes here. That means first length of the pendulum increases and then comes back to same position. So as the length of the pendulum first increases, time period increases, and again comes back to same position, time period again comes to same. That is its situation. Next. When a simple pendulum is arranged in a lift, and here T equal to 2 pi root L by A net acceleration you have to take. If the lift is moving up, G plus A with acceleration A. If the lift is coming down with acceleration A, then G minus A. Net acceleration you have to take. If the lift is moving with uniform velocity, then time period will be same only. If it is having uniform velocity, no acceleration, then time period will be same only. In a freely falling lift, A equal to G and T equal to infinity and so on. When a simple pendulum is arranged to the roof of a car moving horizontally with acceleration A, its time period will be 2 pi root. Why? Because a simple pendulum is connected to a roof of a car and it is moving with acceleration A, then G will be like this. So simple pendulum oscillations inside, if you observe, then effective acceleration A net is equal to square root of A square plus G square will come. That only you have to substitute here. That is this one. And when a simple pendulum is arranged in the roof of a car moving down a smooth inclined plane, then effective acceleration for its oscillation is into the plank which gravity component will act. Into the plank which gravity component will act. This is a car and moving. So this is theta. Then into this, what is the component of g? G cos theta. So that you have to substitute. Square root of L by g cos theta. Okay. And if a simple pendulum is arranged in an artificial satellite, effective g value 0, obviously time period will be infinity, frequency will be 0. If the length of the pendulum is considered to be very large, then t equal to 2 pi root g of 1 by L plus 1 by R, and that is equal to 1 by 2 pi root R by G also will come. If the length of the pendulum is infinite, then time period is 84.6 minutes. And if the length of the pendulum is equal to radius of the earth, then 59 minutes 5 seconds will come. T equal to 2 pi root R by 2G will come. And work done by the string of the pendulum during one complete vibration is equal to 0. And if the simple pendulum is immersed in a liquid, then effective gravity will be G dash is equal to G of, effective gravity is G of 1 minus dl by dB, where dl is density of the liquid or the fluid, whatever in which the bob is immersed. Next, effective gravity will change. Here it's not effect of mass, effective gravity is important here. Next, if two pendulums of lengths L1 and L2 are get into vibrations in the same direction at the same instant when the same phase, again they will be in same phase after a shorter pendulum has completed n oscillations. To find that value of n is given by n minus 1 equal to root over long pendulum by short pendulum. Seconds pendulum, 2 seconds is the time period, and whose length in the earth surface is 100 centimeters, and then decrease, these are all the normal mathematical things. Spring pendulum, restoring force minus kx, time period 2 pi root m by k, where m is the mass suspended to the system. Here two masses are shown in the picture, but actually whatever the mass is suspended to the spring, that mass totally you have to take here. Okay, and we have another formula for time period, t equal to 2 pi root x by g. Practice only time period formula. You want frequency, reciprocal it, but don't memorize both the formula, you will get confused. So time period t equal to 2 pi root m by k. A time period of a spring mass system is independent of acceleration due to gravity. And time period t equal to 2 pi root m plus m by 3 by k. And time period is t equal to 2 pi root m by 3k. What is this m plus m by 3? Spring's mass is also considered. Then m plus m by 3. Derivation is so long, you can learn at higher classes, not at this place. Next. This is very interesting fact. Here, spring constant k is inversely proportional to its length. So k inversely proportional to its length, and kl equal to constant. Kl is equal to k1L1 equal to k2L2 for the given spring, and k1 is equal to 1 pieces force constant, k1 equal to k into L1 plus L2 by L1, k2 equal to k into L1 plus L2 by L2. Next, when a spring of force constant k is cut into two equal parts, each part will have the force constant 2k, two equal parts, then 2k each. Yes, on cutting the spring into pieces, length decreases, so force constant increases. That you have to put in the mind. And when two springs of force constant k1, k2 connected in series, then effective force constant is, yes, you are right, k1, k2 by k1 plus k2. In parallel, k1 plus k2. In parallel, k1 plus k2. The springs in parallel, k1 plus k2. Yes. Next. For the same mass attached to the time period of two different springs T1 and T2, when they are joined in series with the same mass, the time period will be Ts is equal to square root of T1 square plus T2 square. T1, T2s are individual masses time periods, then Ts is whenever they are joined in series, and then like this. Next. When they are connected in parallel, this picture belongs to the second one. 1 by t square is equal to 1 by t1 square plus 1 by t2 square. And time periods of various harmonic oscillations, variety pendulums. See, springs we discussed, and simple pendulum we discussed. Now variety pendulums, what are they? Suppose liquid in U tube is tilted, then it will oscillate with 2 pi root h by g, where h is the whenever the liquid is in equal levels, that height, h is that one. Yeah, h is this one. Picture is there. And whenever a body is floating and oscillating, then time period t equal to 2 pi root m by k, where or otherwise m by a sigma g also you can take, or t equal to 2 pi root l by g. What is L? L is the immersed length, 2 pi root L by g, immersed length, not exposed length, where L is the immersed length. Next, SHM for suppose a trough is there, in that there is a sphere of radius r. That picture I'll give with another color. Suppose a sphere of radius r is placed, then this is r, then its time period of oscillation inside the trough is given by 2 pi root r minus r by g. And whenever a piston arrangement is there, and then if you press it and release, then what happens? It oscillates. The time period is 2 pi root mh by p4. M is mass of the piston, whatever it is going to have, mh by p into 4r, p into volume, right? PV, it must be PV, right? It must be volume, not, yes, as it is, it should have volume, but cross sectional area on the numerator and denominator gets cancelled, so it must be mhpa, area of cross section. We should correct, this is A. Okay, yeah. Next, we'll continue. Longitudinal oscillation of an elastic wire, longitudinal oscillation. Then F is equal to Ya delta L by L. So F is equal to delta L is the displacement, Ya by L is omega square, you can take, or Kx, it can be K, Ya by L is a K. So K is equal to Ya by L, and you can M by K you can take. So that is 2 pi root ML by Ya is time period of longitudinal oscillations of a wire. Then horizontal oscillations. 2 pi root m by k is 2 pi root m by eta L, where eta is bulk modulus of the particular body, and some mercury of mass m is placed at the bottom. It's lightly depressed and released, mercury just depressed and released. These oscillations time period t equal to 2 pi root small m plus capital M by A rho g. And various time periods, various SHMs, When a body rolls and performs SHM on a curved surface, time period t equal to 2 pi root r minus r into 1 plus beta by g, where beta equal to k square by r square. And a body of mass m is released in the tunnel dug in the earth, then its time period 2 pi root r by g only, 84 minutes is the time period for the earth. And for torsional pendulum means a rod or a pendulum is oscillating like this, circular way, then 2 pi root L by c, where c is the torsional constant. Next, time period of a physical pendulum, any solid body is hooked and made to oscillate, any solid body, then 2 pi root I by mgd is the time period, I by mgd. Here important thing is, suppose any body, some body is hooked here and is oscillated like this, suppose it is oscillated like this, then its center of mass is this one, this center of mass, and the point of suspension will give you d, and the whole body is m, and I is moment of inertia about this axis, moment of inertia about that axis only is I, this is only moment of inertia about that axis, I. Okay, next, damped oscillations. Many oscillating bodies do not move to and fro between precisely fixed limits. Continuously on oscillation, it loses energy and the limits will be coming closer. So obviously those oscillations are known as damped oscillations. stretched violin string, after some time it will be stopped, that is a damped oscillation. Damped oscillations equation is d square x by dt square plus b by m dx by dt plus k by m into x. The middle term will come. This is damped oscillation indication. Only first term and last term if present, that is normal SHM. Undamped oscillation. This is damped oscillation. And frequency, that is this is equation. The solution for this equation is x is equal to ae to the power of minus bt by 2m cos omega dash t plus phi, and time what you call omega dash is the angular frequency of the damped oscillator, which is given by k by m minus b by 2m whole square. And energy at any instant of time is given by half ks square e power minus bt by m. And velocity of damped oscillator is v is equal to v naught e to the power of minus pi, and v is equal to v naught by e. Relaxation time t is equal to 2m by b, that is relaxation time. Relaxation time for amplitude is 2m by b, and that amplitude is a naught by e. Whenever amplitude a naught by e comes, then up to that the time, whatever starting to that position, that time is known as relaxation time, that is given by 2m by b. Forced vibration equation will be kx extra will come in that equation, and the amplitude will become f naught by m into, to maintain some angular frequency we need to apply a periodic applied force. So m into omega naught square minus omega 1 square whole square minus omega square and gamma by 2m. So this is formula for that. So amplitude is this for the forced oscillation, and velocity in resonance is given by f naught omega d by m into square root of omega naught square minus omega d square plus 4 omega d square r square. This is the velocity maximum in case of a resonance. Coupled oscillations, that means two blocks are coupled with a string or a spring and made to oscillate. Then in such cases, this is called reduced mass m1 m2 by m1 plus m2. Then time period will be 2 pi root mu by k, where mu is m1 m2 by m1 plus m2. And the first body mass, second body mass, force constant and all. Combined SHMs are governed by Lissajous figures. If two SHMs y1 equal to a1 sin omega t, y2 equal to a2 sin omega t plus phi, then y equal to y1 plus y2 or a sin omega t plus theta, where a is equal to square root of a1 square plus a2 square plus 2a1 a2 cos phi, theta equal to tan inverse a2 sin phi by a1 plus a2 cos phi. X is equal to a1 sin omega t, y is equal to a2 sin omega t plus phi, and then the combined SHM will be, in this particular case, combined oscillations equation will be x square by a1 square plus y square by a2 square minus 2x1 xy cos phi by a1 a2, that is equal to sin square phi. So various cases will come with the variation of phi value here. And so these are all Lissajous figures actually. You can practice. These are all formulae, and you try the worksheet problems first, and I too will discuss worksheet problems. Then you can correlate with your answers with my answers. Later you can practice lecture sheet also. Thank you dears. Worksheet questions session will be followed. Bye.